everyone. Welcome to another video. Alright, let's turn down that music. Alright, welcome to the anticipated sequel that we have. Here it is. Our sequel to the Analog Fourier series. So, yep, it's April 1st, by the way. So someone told me that a certain professor did digital first and not analog. So I was supposed to make a digital video first. So rip, I'll have to make that eventually. But I will focus more on analog because the next exam that we have right now, it's coming pretty soon, is on the Analog Fourier series. But before we go over the Analog Fourier series, we got to go over something that's really related to that, and that is your assignment. And I've already gone over it a little bit. And if you haven't seen the last video was me going pretty brief. I was really brief on how to actually just start this assignment, and I showed you how to do the Gramian, what's going on, how to get the Gramian, how to prove the Gramian, that these are our weights, the alphas are weights. It's basically saying, oh, this basis set right here is this heavy, or we need this much of this much of this, and it just determines how much of these basis functions, or these the product, dot product of this, how much do we need of it. By now you've probably already seen how to do this. This was pretty fun, pretty straightforward. And now the focus I want to get to is this bad boy right here, which is basically, oh, now we got to do a Fourier series. So the generalized Fourier series as well, I'll just show you right here on a piece of paper. Do you like full screen or widescreen? Haha. Yeah, someone complained saying, why didn't you do like a full screen? I was like, oh yeah, you're right. So the point of the generalized Fourier series is basically if we had a projection, let's call it F, of what's it called? Let me see. F. Do they call it something here? No, they're just, oh yeah, f of t. Sweet. F of t. Oh, you want large screen? Is basically equal to, you know, some weight alpha 0 at some beta or b0, which is a function of t, plus a1 b1 as a function of t, and dot 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 of a of n n minus 1 b of n minus 1 t. And the reason why I put n minus 1 is because we have 1 2 3. If n was equal to 3, that means it's 0 1 2. So elements, how many functions do we have? And this is general, actually. This is the series function, which is basically from n is equal to 0 to n is equal to n minus 1 of alpha n b of n t. And this is your generalized Fourier series. But for the exam that you're going to be seeing, we want to know the exponential Fourier series, which is, I'll define it as, let's use a different marker. Aha. My orange marker. There we go. So let's do this. So for the exponential Fourier series, the definition is basically we're going to look at n is equal to, or actually, okay, let's be consistent with the book. K is equal to minus infinity to k is equal to infinity. So we're taking a whole bunch of signals of c of k, let's call that k, and e to the minus j, what's it called again? J omega. Do I want to call it k t? I think that's how you write it. 2 pi k t. Yes. So this is it. And you're probably saying, gee, David, how'd you get that? So we're going to go over the basic definition. So if you wanted to find what this is, actually, I'll just define our basis function. So our basis, if you can probably tell, of k is equal to, well, e to the j, yes, positive, omega k t. So let me check. I'm trying to make sure my notes match. All right, yep, this is it. So This is our basis function that we're going to be using in all these things. So the definition to find this weight, so if you see from here, we have alpha of k, which is equal to this divided by that. So in a way, we're going to do this. So c of k is going to equal f of t, b of t, k of t, divided by bk of t, bk of t. And that right there is your definition of how to even approach this or how to do this. So, and you're probably saying, hey David, why did it look, why do we have this negative? Well, if you recall, when you do this little dot product, you multiply this, well, you take an integral and you multiply this by, it's the conjugate of this, so you just conjugate this, the conjugate of e to the j omega kt is minus, so that's where you get that minus sign. So is it making sense right now? No. All right, so the next thing I want to do is the assignment. And yes, I'll go over the solution to make sure you know what's going on. You can do this on the assignment, on the exam, sorry. And you can sing Kumbaya and be pretty happy. So we're going to do this, and you can do this as a homework. Well, it should be homework. So I'm going to bring out another piece of paper. This is page 1. Go. And let's grab another piece of paper. So the function that we want to map, this function that we want to map is the e to the t, right? Yeah, I'm already forgetting. It's pretty late too. E to t from 0 to t. Are we including the dot? Yes, we're including the point. So we want to find the exponential Fourier transform. So the definition that we have is ck is equal to f of t and e to the j omega wait, k t. I think that's it. Wait, I'm trying to follow my notes right here too. Yep, that's correct. Divided by e to the j omega kt, e to the j omega kt. So the first thing I want to solve for is this puppy right here. There we go. Nope, that's a bad color. No, that doesn't even match. Yeah, let's go with black. There we go. So we're gonna try and do this little function so you know what to do. So to do this, ej omega kt, ej omega kt, and I'm assuming you probably don't know what's going on, so we're going to try and show as many steps as we can. So from t is equal to 0 to t is equal to 1 of, well, e to the j omega kt times e to the minus j omega kt and dt, because we're integrating with time. So if you see this right here and this right here are the same with, well, this is a it's conjugate form. So if you just multiply this by this, okay, because I'm assuming some people don't like signals, on e to the, since actually, okay, I'll do this, j omega kt minus j omega kt. All right, now do you see that? What happens to this? This turns to 0, and that means you got e to the 0, which means this is all 1, which means you're going to get 1. So this right here is the pure definition of like the entire class. Actually, there's another thing I got to mention. Do I want to mention that? There's a rule that we have to establish too, where omega, why did I write omega here? It's actually equal to 2 pi over t, where t is our period. Right now, it doesn't really matter that we have this t. Well, yeah, it does, because Dr. Stewart makes it to where t is equal to 1, so that means you don't have a pesky t somewhere there. But point is, this t is always there. Memorize this. It might come up in an exam. I don't think so this exam. Actually, it will. So memorize this one. Put it on a cheat sheet if you need to. So, but point is, you get 1. This right here, this is a definition that you gotta memorize. So now that you know that, let's do, let's choose this marker. Let's do this bad boy right here. And well, yes, we're doing the assignment. So if we wanted to do this, to skip steps, I'm going to do the integral from t is equal to 0 to t is equal to 1 of our f of t is equal to e of t, and then times e to the minus j omega k t. There we go. So now that you have this right here, you can just do the multiplication. And because it might be a little hard to see this multiplication, we have to actually do it. Let's do 0 to 1 of e to the, because the t's are similar, I'll just do this 1 minus j to, actually, do I want to do this? So I'm going to do omega is equal to 2 pi divided by t, but t is equal to 1. And I'm going to do 2 pi of, so this right here is this guy right here. So that's what I'm doing. 2 pi k t. Boom. Oh, my microphone popped. dt. So now that you have this happy little integral, I'll just do this because I think someone's going to get afraid. Don't be afraid. If we call some constant q is equal to 1 minus j 2 pi k, that means you can have 0 to 1 e to q, which is a constant. This is a constant. T dt. So what do you get? You get flip 1 of q. The q comes down here because we're integrating e to the q t from 0 to 1 because we're doing t. And that is going to equal, putting this puppy back in, I'm going to have 1 minus j 2 pi k. And do we want to do this? Okay, yeah, let's just show the steps. It's basically e to the 1 minus j 2 pi k, because this right here, actually, this qt exists, so that means this right here exists, actually. I did not explain that one. Okay, e to the 0, so q times 1 is, well, that's the variable I called it. See, I'm just calling variables. But now we're going to do e to the constant times 0. That's, this whole thing is 0, which means e to the 0, that's just 1. And then we're going to get our happy little signal right here, which is, yeah, let's do this. 1 minus j 2 pi k, and then times e to the 1 minus j 2 pi k minus 1. And there you go. This right here is your solution to your Fourier series, your exponential Fourier series. And the next thing we're going to do is, well, we got to use this. So the next trick I need to show you, because I think someone's getting lost. I don't know. From the last video, everyone's like saying, why didn't you just do the cooler way? But I'm going to show, or like the obvious way, which is a for loop and using like a whole bunch of functions. But I'll show you another way. I'll actually show you some MATLAB. Just put this paper right here. Here we go. So now that you have your Fourier transform, you're about to do your projection. This is a proj right there, which is equal to, well, if you wanted to do this, c of 0, and which is defined by this guy right here. Well, your function, this is your c's, times your bases function, which is basically e to the j 2 pi, I'm just going to do this right here, 2 pi 0 of t plus c of 1 e to the j 2 pi of 1 t. plus c of 2 e to the j 2 pi of 2 t, and then dot dot dot, and do it for here, plus c of minus 1 e to the j 2 pi minus 1, oops, t, and okay, I'll finish it. C of minus 2 e to the j 2 pi of minus 2 t. So this is just a portion of what you're gonna do, and what you would probably do in MATLAB, and I don't blame you, is probably this. You're gonna probably do like proj is equal to a whole bunch of you're probably gonna put your c of 1 and then your basis function b of 1 plus dot 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 c of 2 b of 2 plus dot dot dot, and then down the line. That's a lot of lines. Like if you have to write 15 codes a line or lines of code, it's going to be pretty long. But there's a cool trick that I want to show you. So let me see if I can remember, because I have an example I want to show everyone. Let me see if I can pull this one out. Oh yeah. Actually, wait, let me just check it on the side just in case. Actually, I can show you this example. This is probably what someone's going to be doing, where they get their weights, and this is for this is the example 2 on computer assignment 2, where someone just does this, and then they do the projection, and that's your vector signal, and then you just plot it like this. That works, but this is painful. But what I want to show you is, wait, let me see if I get this right. Okay, F. Okay. So what we're gonna try and do, oh, this marker is already dead. So if you were to define a vector t, which is equal to 0 dot dot of 0.01 dot dot 1, and you were to call some function, or your f, or whatever your thing is, your signals are actually, hold up, I'm trying to think. No, these are your basis functions, like, yeah, I'll just call it bases. And you want to have it as a vector of time. So t, or the length of t, length of t by however many signals you have, which is 2n minus 1. There we go. So for example, let's say n is equal to 5. That means you're going to have, well, I'm going to draw for you. So for the exponential Fourier series, if you have n equals 5, that means you're going to have 1 right here, and then you're going to have 1, 2, 3, 4, 5 on the right and 5 on the left. And then you have that in mind. So 2 times 5 is 10, minus 1, that's 9. So that means you have 1. Actually, I think this is going to be 4. I think that's definitely right. N is equal to 5, 0, 1, 2, 3, 4, 5. Never mind. The point is, you're going to have 0 and minus 1, 1, and then minus 2, up to, I think this has to be 5 or 4. Let's just say 5, minus 5 and 5. You're going to have double the signals. So that's why I have this right here. So your, let me see. There we go. These values right here, you're going to have a vector c, which is basically a vector which is 2n minus 1 by 1. So you're going to have a huge c vector, which is going to be your c of 0, or c, or weight 1, c2, or dot dot dot, but it's just going to be 1. It's going to be if we had 3 weights, so if we have a 3 by 1, and actually let's not do that. Let's stick to this example. N is equal to 5, so 2n minus 1 is 9. So if we were to have a 9 by 1, and then this would be a let's call it 1,000 points by 9. So what I'm going to do is your projection is equal to, we want to have 1,000 points times our 9, and then, well, you multiply, you do the matrix multiplication, a 9 times a 1. And your resulting thing is, well, these two 9s right here, when you do matrix multiplication, they combine. That means your final result is going to be a 1,000 points. I'm assuming T is going to have like 1,000 points in it by 1. And that right there is your signal. That right there is how you're going to calculate. So instead of doing this painful mathematics, you're just going to do this, which is your basis functions, whatever you do right here, these guys right here. Actually, no, just boxes right here, boxes right here, and boxes right here, which is going to be tied to this. You like that spaghetti? That's going to be that. And then your C's are going to be, well, this, and this is how you would do that mathematics. So just in case you didn't know why people were doing this multiplication, they were doing B times C, or your bases, or whatever you call it, B cross or matrix multiplication by this. It's a really fast and simple way of getting things done. So let me see. Back to what I was gonna talk about. If you wanted to plot this, actually, I think we can just go into, yeah, I'll just show you the MATLAB. Let's go out here. And I'll show you two answers. The first one's wrong. Well, it's right, but the second one is what you should be trying to do. So this right here is your simple solution. So right here, and I'll just put this down right here, is, well, n is equal to 5, but I think, yeah, I think I made a wild mistake. What was I doing here? And from 1 to there. But point is, I was doing this. I was doing the multiplication like through MATLAB. This is not the right way. Don't do it this way. If you do it like this, yes, you will get marked off a point. Not by me, but by Dr. Seaver. Yes, he took off a point. So don't do this. This is bad. This right here is bad. I'll just do that. Now, this is what you should be doing. Let's do 5. And we're going to walk through this. So first things first is you have to have clear variables. Second things is just in case you have OCPD, do CLC. That clears the command window. Then here's your n. Then here's your vector of C's, which is going to have 2 times n minus 1. So that means we're going to have a DC term in the middle. And we're going to have up to, well, 5 signals on the left and 5 signals on the right. I think that's it. No, let me see. We have, actually, now forget it. Let's just go through this. So we're going to go from, I think I know what's going on. If we're going from 5, minus 5 to 5, that right there is, we have 1, 2, 3, 4, 5, 10. We have an 11, a length of 11. So actually, this gets overwritten. Oops. Well, point is you can do this. Actually, no, I have a great idea. And this will work. Minus 1. Minus 1. Boom. So one thing you got to do is, okay, I got to explain to you what this means. So actually, let's go back to your piece of paper. So, okay, that's this right here is page 3. And let's pull out this guy right here. So we want to know what happens to our Czk. Actually, I'm going to write this on another piece of paper. You guys are probably saying it's too messy. There we go. I'll write it on another piece of paper. Oh, too much paper. Go. There we go. So C of k, this is what you're going to be writing in MATLAB, is going to equal to 1 minus, or 1 over 1 minus j 2 pi of k, which is e to the 1 j 2 pi k minus 1. So what happens at C of 0? This is our DC term, which is going to equal 1 divided by 1 minus, well, this right here is going to be 0 because 0. Then e to the 1 minus 0 minus 1. And let's see. This e to the 1 actually, oh, I actually made a mistake then. It's going to equal, well, that's just gone. E, actually, why does this term stay here? E minus 1. Well, I think I did something wrong then. Yeah, that can stay. But yes, that's your DC term. And let me just check, because that's bothering me now. I think I made a mistake. This should be, maybe I should have just kept it like this. Boom. Let's nope, let's actually, yeah, let's just run section. Why do I have this right here? Actually, yeah, let's run that. Oh, it's barking at me. Why? Perform elemental multiplication. It doesn't like this. Let's see. Let's look at the other warnings. Error using this. Okay, you're seeing what I'm seeing, right? Ah, that's because this is 10. This is 1 by 10. There we go. Wait. Okay. What's this generating? F9. Hold up. That's 4. Okay. And then this should be 4. Ah, I know what's going on. I gotta do the same thing right here. It doesn't like that. There we go. -1. And don't worry, I'll go over what that means too. Run section. Okay, it doesn't like me. Oh, because I did the same thing here too. Oh. -1. Don't worry, I will save you all. I will carry this class again. Why is it barking? X must be the same length as Y. Okay, it's saying something. It doesn't like this. Abc. Okay, so what is this? So this right here is that's 4 minus 4 to 4. That's 8 plus 9. That's 9. That means C has to be a 9 elemental matrix. There we go. Let's hover here. 10. So what's going on? Oh, it's already too late into the video. Oh no. Nope. Wait. Oh no. Here we go. Yeah, I don't like troubleshooting. Projection. Abc. N-1, N-1. That's 9. This result right there works. That result right here works. Why is it not letting me do what I want it to do? Okay, let's just get rid of this. Maybe it doesn't like that. Alright, because I want to know what's going on. There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, it's not plotting the final point. 4. Okay. Something's going on right here. Well, okay, back to what I was doing. Aha, that's what you should be looking for. That looks more right. And then if you wanted to do this, you can do the following, where you can have your f real is equal to e to the exponent of t. There we go. And then you can plot that puppy right here, t, and then f real. Oh, there we go. And boom, looks pretty good. So that's how you do that part of the assignment. And I want to troubleshoot this one, but I don't want to spend so much time on this. But you know what I mean, right? I'm missing something somewhere. But okay, that's 4, 4, 4, 4. Why is it barking at me saying, okay, this is 9. 9. We have 4 on one side, 4 on the other. Why is it saying 1, 2, 3, 4? Oh. I think I know what's going on. It's adding this point, but I don't want it to add that point. 4. Okay. What if I do this? Actually. Okay, 4. That's 4, 4, 5. No, that's -4. -4, 5. Oh, see it? There we go. I'm a mastermind. Haha, works. Got it. See, you guys all doubted me. Boom. Boom. All right. You guys can show this to Dr. Stever and be like, yeah, we know what's going on, Dr. Stever. And haha, look, it's normalized. This is exactly what you need to see. Normalized. That's exactly what you need to see. If you don't have this normalized, force it. And that's doing this. Oh, I showed you the answer. Let me show you what this does. Yeah, because that's E minus 1, which makes sense. 2.7 minus 1 is 1.7. So to normalize it, make sure you do this, and you should be set. So that's your solution. That's how you do it. So sorry that took so long. You can do this doing the same method that we just did right here. So we just did. So number 3, show your hand calculations, because that's the whole point. That your hand calculations is literally this. That's your hand calculations. So Dr. Stever wants to see that. And then 4 is literally putting your hand calculations to the test. And then this one, well, easy, just change this time and you should be set to go. So that's the entirety of this assignment. So hopefully you guys like that. But now let's go over the fun part, which is your exam. And I want to go over another problem. Let's do this. It's 2, 3. I mean, this has to be page 4. Actually, you already got that one. This is your DC term. So now I want to try a nice signal. There we go. So what if, wait, there we go. Hold up. Let me try to look at something quickly. All right, what if I had the following signal, which is going to look like this. So let's just say it's amplitude here. This is going to be f of t, and we're going to have it from minus t, delta t of 2, to delta t of 2. So what if you had to do this signal and you were asked to find the Fourier transform? And that's simple, the Fourier transform. And the definition is, well, f, I like writing my f's like that, j omega is equal to, you're going to look at the entire signal from, or t is equal to minus infinity to t is equal to infinity. So you're looking at the entire signal. You're just sampling that entire thing and just seeing what information it has. So we're looking at the entire signal, and we have to multiply that by e to the minus j omega t dt. So this right here is a rule that you have to memorize. It's a holy grail of like everything. If else you won't be happy on the exam. So to find the Fourier transform of this happy little signal, all we gotta do is, well, just punch in your signal. Look at the time. We only exist for this. Therefore, your Fourier transform f j omega, it's a function of j omega, is equal to minus delta t over 2, delta t over 2, of 1. It's literally just a 1 times e to the minus j omega t dt. So now I guess everyone knows how to do this by now. We're all pros at it. You just take this guy, divide it by that guy, and e to the minus j omega t. If you don't trust this one, take a derivative of this. You get that. Of minus omega t over 2, delta t over 2, and this is going to equal 1 minus j omega, and e to the minus j omega delta t over 2 minus e to the positive j omega dt over 2. So if you aren't screaming by now or bells aren't ringing, this is actually looking like something pretty familiar, and I want to really stress this point out. So that one was 1, 2, 3. I'm trying to find my other papers. Actually, no, this is 4. I said this is 4. Okay, so I'm going to put this guy right here. Don't worry, guys, I'll carry you. This should be like a huge mega review. All right, there you go. So let's rewrite that again. The Fourier transform is equal to 1 minus j omega. I will do, actually, okay, you see this right here? I'm going to multiply the negative inside, so if you don't like me switching terms, I'm going to do this. E to the positive j omega dt over 2 minus e to the minus j omega delta t over 2. So this right here should even look more familiar, and this is our introduction to, well, Euler's equations. So we're going to do a sign. So if you see this, e to the positive, you have a positive frequency minus its conjugate, you get the sign. But to do that, you have to multiply top and bottom by 2 and 2 because we have a j. We required a j. I will show you the work. Okay. So for this to work, we have to, we need this j, we need this 2, and then this whole thing will transform into, and we'll choose different markers. So actually that positive goes away. We have a 2 that stays here because this residue, and then the term that we get is sine, oh, we have a w there too, sine of omega delta t over 2, and I'll do this because we have that w, and there you go. That is your Fourier transform, or your Fourier transform. Yep. So that's how you get it. And then they ask you, all right, I want to know the Fourier series of the signal that we have right here. So there's a couple cool ways you can probably approach this problem, but one of them, and this is the easier one. So let me see. So recall that Fourier transform. If we take a sample where omega is equal to 2 pi of t, we're kind of sampling the Fourier transform in terms of n. So let me just do that. However, actually, no, let's just do this. So let's sample this guy right here. So if we take this guy that we have, we're going to do a 2 sine and just replace all the w's you see with 2 pi of n divided by t, and then times delta t over 2. There we go. And we have a w down there too. It's annoying us. So let's do 2 pi of n divided by t. And we'll do this because everyone likes colors. Boom, boom. That t goes away. That t goes away. This kills that. That kills that. And what we get left is t sine n pi, that delta sign, and pi event. And then you're like saying, oh, we have a pesky t. And that's not bueno. So one thing you need to know is we want the Fourier series. This is well, we're getting the actual Fourier transform. We're getting the Fourier thingy, but the definition of the Fourier series, which is C, which is equal to, well, actually, yeah, I'll do this. The Fourier transform itself, omega sample data, omega is equal to 2 pi of Tn divided by t, because you have this basis function. So this right here looks similar to, oh, sorry, where'd it go? This right here is our f and our basis function. This is basically that. If you don't remember, this Fourier transform used to look like the integral of f times your bases, which is minus e or something like that, minus and or t or whatever. But this is what this is going to look like. This right here, this top right here looks like this, and then this bottom right here looks like the the dot product of this, the inner product. I think that's what he calls it. So that's where this t comes from. So if you were to do this, the Fourier series, we want the c's, we want the weights, is basically the Fourier transform, which is sampled at this time, divided by t, and your final result is sine n pi divided by pi, and there you go. That's how you solve for that little problem right there. Okey-dokey, and that's how you do that problem. So the next thing I want to do is, let me check my holy notes. Let me see. Oh. Go. There is a second way that we could do it. Well, the second way is basically, you know the c's, and you know that it's going to equal this f and b divided by this b and b, right? Which is basically equal to 0 to 1 of f e to the minus j to omega k t or something like that, divided by t. Oh, so that's your second way. So you can either do it by sampling this Fourier transform, or you can do it this way. So there's multiple ways of doing it. So you can do it this way. You can do the same thing. Like you can do this math again. Here's the math, and then divided by t. Or you can sample the Fourier transform at this condition right here. So that's how you do this problem. So the next thing I want to do is, that's page 5, right? And study the other variants. I think there's a sawtooth wave, or a signal that looks like there's other signals. You probably will have you'll either have this signal, which here's the time 0, and I think this right here is delta t of 2, and then this right here is delta t of 2. Or you might have a signal that's like this. That's a sawtooth. Or you might have another signal, which is here's signal f of 1, f of 2, and f of 3, which is equal to, maybe you might have a backwards saw. Maybe you can have a backwards saw. Or actually, maybe it's not even a saw. It might be a triangle wave. It might be a triangle. F of 3, which is a triangle, where it looks like that. So be wary. So if you can do this, and you can do this signal right here, and this signal right here, and this signal right here. Oh, I can't show you right there. That right there. then you should be golden on this exam. That's the whole point of the Analog Fourier series. So the next thing, let's grab another piece of paper. Go. Oh yeah, maybe a quick tip. If you wanted to make a trigonometric series, and let me look at my notes, a trigonometric series, all you gotta do is you gotta look at this minus one right here, and then you look at this positive, and you combine them. That's how you get the trigonometric Fourier series. So the exponential can turn into the trigonometric if you just fold it. So you might forget that one, but remember that one. Totally not a exam question. So that's how you do the trigonometric. The next thing I want to do is, let's look at the holy notes. Let's actually do Fourier transforms. There we go. This is page 6. That's a small 6. So what if you get a signal which is x of t, which is equal to e to the alpha t. So we want to find the Fourier transform of this. But before we do the Fourier transform of this, remember the Laplace transform, or old little buddy Laplace? So remember when we did the Laplace transform of a function f of t, we got some crazy stuff. And remember the Laplace transform of e to the alpha t? That's basically equal to 1 over, was it 1 minus a? Oh gosh, I'm forgetting now. No, s minus a. There we go, s minus a. So that's how you would do your Laplace transforms. There you go. So if you wanted to do the Fourier transform, the easiest way, and this is what all people do actually, I'll draw a picture right now. So the Laplace transform, you're going to have the Laplace of s. This is the s domain, and maybe your pole when alpha is equal to when s is equal to alpha, which has got to be I don't want to put it here because the pole has to be on the other side. S is equal to a. But point is, we want to look at this imaginary axis. This right here is the Fourier domain. F of s is equal to j omega. So this right here is the point that we want to get to. That bothers me a lot. Let me check my notes again. I think it should be plus. I think this has to be plus. Yes, this has to be plus, because the only way for this to exist if this is s plus a. Yes, it is plus, sorry. So that means, yes, the pole has to be on the left side. Has to be on this side. If you have a pole on the right-hand plane, it goes unstable. The minute this pole crosses the imaginary axis into here, here's the right-hand side. Remember that? It would go unstable. You don't want that. You want it to be on the left side. So for stability, your poles have to be on this side. And the region of convergence has to be, well, on this side too. But point is, this pole play effects on our Fourier transform. So to get the Laplace transform and the Fourier, all you got to do is just literally this, which is equal to the Fourier transform. Fourier transform j omega is basically the Laplace transform at s is equal to j omega, which is basically 1 j omega plus alpha. That's it. And yeah, that's literally it. So now you know how to get Laplace transforms and Fourier transforms. But I want to do another problem. The problem I want to do is, what if you get x of t is equal to e to the alpha t? So now you have this situation. But we know, as engineers, this is equal to e to the alpha t. And let me remember this one. This only exists at u of t, and then e plus e to the minus alpha t, and this only exists on this side of the spectrum. So this gives you this. So knowing our Fourier Laplace transform, let me look at my notes again. Go. I want to make sure you guys know what's going on. There we go. The Fourier transform, actually. Laplace transform of x of t is equal to, well, 1 over s minus a plus 1, wait, I think, was I right the first time? I think, wait, s minus a when a is equal to 1. No, I'm trying to look at this right here. This right here. That's bothering me. Yeah, this should have been minus. That should have been minus. But give me a moment. Give me a moment. Oh yeah, I was so dumb. I just had a wild guess. Sorry. Point is, there we go. Why was I doing this? Yeah, it's okay. Whatever. Divided by 1 s plus a, or actually, this should be minus. Should this be a minus? Yes, this should be a minus because we have this negative term and then we have this term that pops out. We get a minus because of this dumb little thingy. And this only exists, and I don't know if I want to draw these poles because I don't remember it actually. Which is going to equal real part of s. This is only going to equal this right here, alpha. This function is going to equal, exist when s is greater than this a. And then this right here is going to equal real of s has to be less than minus a. So we're bounded by some little points. So this is how you do this. And if you wanted to know the spectrum, which is the Fourier transform is equal to the Laplace transform of s is equal to j omega, which is equal to actually, why am I forgetting something else? Oh yeah, you can also combine this too. Actually, get rid of this line. Yeah, I did the math, and you get this 2 alpha s squared minus a. Because if you multiply this and this in the bottom, you get, well, this and this. Then these two combine to get you 2 alpha. So now that we have this, we're going to get the spectrum, the Fourier transform itself, and just replace all the s's with j's, and then you get 2 alpha, and then you get j omega squared minus alpha squared, and then that's equal to 2a minus omega squared minus alpha squared. And because we don't like these minuses, you can do minus 2 alpha omega squared plus alpha squared. That's your Fourier transform. And there you go. And then if they ask, all right, you got to draw this puppy. Well, we know when omega is equal to 0, or I think, yep, omega is equal to 0. So if f of 0 is going to basically equal minus 2 of alpha divided by, well, 0 plus alpha squared, which is equal to minus 2 of alpha. And you know this, that this, as w gets bigger, that means this starts getting, the denominator gets bigger, and that means the entire number gets smaller. So if you wanted to do the magnitude response, yes, this is the actual magnitude response of j omega. This is how you do your Bode plots too. You can do right here, which is that amplitude, and then it probably just go down like this. You can draw a better one. This is the omega axis. So that's how you do this problem. That's how you do a simple Laplace transform. Memorize the other ones, e to the at. Maybe you might get a shifted one, or you might get a cosine or a sine one. Those ones are fun. So that's how you do that problem. This one's page 6. And now I want to do one more nice study tip for you guys. And let's do actual circuits. Let's do like, okay, we're gonna actually do real engineering. So suppose you were given some RC circuit, RC, which is d of y of t dt plus y of t, which is equal to the x of t. This is the equation for the RC circuit, a simple crossover filter. So let's say I want to know what the magnitude response. We're trying to look for a frequency response. So you know what that looks like. You're like, oh, you got Bode plots, you know, h of j omega, and you have this, and you have some f3 dB, like, you know, and then this is 20 log if you wanted to do that. But we're gonna do this. So remember the Laplace transforms when we were able to well, with the Laplace transforms, we were able to, if I were to do the Laplace transform of a derivative dy for dt, you actually get s and the actual y out of here. So it's the same thing with the Fourier transform, except for the Fourier transform, you're going to sample it at when s is equal to j omega, and there you go. S is equal to j omega, which is equal to j omega y j omega. So applying this little rule, you're going to get RC. So into the Fourier domain, you're going to get the RC, and then we know our little trick, which is S, then I'd like to do capital Y, j omega, plus, well, what's the Fourier transfer of y at t? It's literally j omega is equal to x of j omega. So recall that the transfer function, or your frequency response, is equal to the output divided by the input. Therefore, we want to do some crazy math. So if we do y j omega, basically src plus 1 is equal to x j omega. Therefore, our h j omega is equal to y j omega x j omega, which is 1 over src plus 1. And guess what? That's literally the equation for your simple RC filter. Pretty simple, and you can do a lot of things with this. There we go. So the next thing we want to do is I want to put a signal here. I want to put a signal x of t. And the signal x of t I want to put in is, let's see, we're going to input a DC signal and a periodic signal. So let's say x of t is equal to 1 plus, let me look at my little notes. We're going to put this 2. Oh yeah, we're going crazy. So the whole point of spectral contents, or looking at a spectrum, is we want to know the information of a signal. So I'm going to talk to you on a practical purpose. So from a music perspective, if we have a DC signal, well, a DC signal, if we were to look at a spectrometer, you know those music spectrometers, or if you try to sing and you see like, oh, you see the Fourier transforms or the thing, literally our DC signal is going to be, and I think I'll use a blue marker, our DC, this right here is DC. It's literally going to be this point right here. It's just going to be right in the middle. And suppose I had a frequency, let's say f is equal to 1 kHz, and we were doing a spectral content. What is this going to look like in the Fourier, or the spectrum? What's the spectral? What's this going to look like? And literally at f is equal to 1 kHz, it's just going to be literally a spec. However, with the Fourier transform, we actually have an equal and opposite effect right here. We have an f is equal to minus 1 kHz. And this is a very important topic when you get into communication systems. So you get a spec that comes up here and right here. And there's that's basically the synthesis of like music. So if you wanted to play like this type of note, you literally get this note like 1k hertz. I think that's a C. I know 440 is your A note, and this is your frequency of F. We're calling it the Fourier transform, your spectral. So the point that I'm trying to get to is if you wanted to get, that's from a practical purpose. Now you know what you're looking for. You're looking for literally these specks or these points. That looks like a Dirac or a Dirac or Kronecker or whatever you want to call it. Delta, a delta function. So that means x of j omega. There's a rule. So, well, this right here is, well, just DC. If you look at the notes, there's a theorem and it's super long, but you have to memorize it. This is a DC term. It's literally DC. It's going to be a spec. When omega is equal to 0, this works. However, it's multiplied by some function, 2 pi. And then for this guy, actually, I have to do this. This 2 cosine is actually going to equal to, let me do this. Hold up. E to the minus 2 or plus 2 pi or 2t plus e to the minus 2t. So same thing with this. These are literally going to be specs on your thing. So actually at f is equal to 2, you have a 2 hertz signal. That's a pretty bassy note. But you're going to have 2 specs. And what I'm going to do is you're going to have 2 pi. And when does this thing start? It's going to start at d omega minus 2. So when omega is equal to 2, that's the positive frequency. And then plus d or delta omega plus 2. So this is the positive frequency. And this is the negative frequency. And there you go. That is your spectrum of your input. You have a spec right here, this delta here at DC, your DC term, and then you have a delta which is here, and then you have a delta right here. Well, f is equal to 2, f is equal to 2. Yeah, that's your 2 hertz signal. So now you're like, okay, David, let's see. I want to know what the output is, or what the output of this system is going to do. And that's pretty simple to do. So to get the output spectrum, y of j omega, it's literally just, well, your transfer function, j, hj omega, and xj omega. And all you got to do is literally just multiply this right here by this right here. So actually, just box that guy here. Oh, I'm just writing everywhere. Super late. This times this gets you this, and that's a literally easy answer. And now, actually, I'm gonna write that out too. So your answer is gonna literally be 2 pi Dirac delta at the DC term plus the Dirac delta at the positive frequency and the negative frequency divided by 1 plus j omega rc. That's your spectrum. Now I want to know what this is going to look like in the time domain. And the beauty about this is, remember the Laplace transform? There was a weird, actually I'm going to do this on another piece of paper. This is page 7. And this is going to be my final one before I shut down. Page 8. Remember in the Laplace transform, there's a simple thing where y of t is equal to, well, we're going to look at the Laplace transform at like some point, s is equal to whatever point you want, e to the minus s of t. This is literally your Laplace transform. Actually, this right here is the pole, a pole. Actually, no, the real function. Actually, just do this. In reality, it's going to equal to some residue, e to the minus pole. So that's literally, and then plus whatever poles you have in there too. So same thing. This is Laplace. Same thing with the Fourier transform. So y of t, but this is actually much more easier, is going to literally equal your input times your magnitude response. H j omega e to the j, the angle h j omega. There we go. So what's this gonna mean? So suppose I were to draw, actually I'll show you practically. If I have an input, let's say x is equal to some frequency, it's a sine wave, sine of 1 kHz, and I have an RC or an F3 dB, which is equal to 10 kHz. So we're literally doing an RC circuit, so you already know what this is going to look like. So we're going to have some gain, and then we're going to have our thing right here, and it's going to go down to whatever value it has to be. So here's our 10K and our X signal. If we want to know what the output is, all we got to do is, well, multiply our input signal, our 1 kHz kilohertz signal, by the transfer function itself. So literally, if you want to know, like, it's like voltage in, your V out divided by V in is equal to your gain. Therefore, your output is equal to your gain times your input signal. So V out divided by V in is equal to your gain, or your output, V out, we're literally doing Bode plots, is equal to your gain times V in at that frequency, at F is equal to F naught or whatever. So G, this gain or whatever you got at that frequency, multiplied by whatever your input is. So that means if your input is a very fast signal, like right here, multiply that to this low pass filter, it's going to get filtered out. And if it's a low signal, if your input's a slow signal, multiply that by a gain of unity. I guess this is going to be a gain of 1. But point is, this is literally that. So therefore, our input signal is going to be, let me do this, 1 times hj omega times the phase. Let me just pull this guy out right here. If you look at, let me remember, h is 0. No, there's nothing. It's literally DC. Since we have a DC signal, our input, if we put a voltage of 1, let me just rewrite this. I'm trying to make this practically make sense. If I have a voltage, 1 volt at DC, what's the voltage out here? The output. It's 1 volt. So that means your Y is literally going to be just 1 plus h j omega e to the j let's see, j angle h omega plus our input X is going to have one of these guys. It's going to have one of these frequencies right here. I got to write this out because I don't want you guys getting confused. X is equal to 1 plus e to the minus 2t plus e to the positive 2t. So we have 2 signals. So this right here is going to be at omega is equal to 2. And then when we multiply our transfer function by our input, this guy right here, we're going to get minus j minus 2t. Yep, I think that's correct. Yes. Then plus h, I'm going to write this, j of minus 2 e to the j of h, the angle of h of j minus 2 plus j 2t. So if you do that, if you punch in your numbers right here, let me do this. Let's see. Do I want to put it on there actually? Okay, which is equal to 1 hj at 2. We look at this guy right here. This goes to 0. That works. That goes to 1. That goes to 0. So that means you're left with. Let me do this. Hold up. Am I forgetting a 2 somewhere? No, that should. Nope. No. Actually, don't look at this. Look at this guy right here. Yep, this RC circuit. I was looking at the wrong thing. Plus, I don't know why I was thinking that. 1 over j omega RC. Hold up. I will get you through this. J omega RC plus. Nah, that was terrible. 1 plus. This is much easier to understand. 1 plus 2 squared is equal to 4 RC squared. Then you're going to have your angle, which is angle tan, whatever this was. The angle of this function, oh gosh, I think I'm going to have to use another piece of paper because this is just getting messy. There we go. Let me write everything out. Sorry if this is taking a little too long. We're at an hour. H j omega, which is equal to 1 over 1 plus j omega RC. And then the amplitude, the magnitude response, j omega, is equal to 1 over square root of 1 plus omega RC squared. Okay? The angle of hj omega is equal to, well, tangent minus tan minus 1 of square root of 1 plus omega RC squared. There you go. So now going back to our input signal, which is basically equal to 1 plus whatever the transfer function of this at 2. Let me do this. H, or 1 over 1 plus 4RC squared. Angle minus tangent. 1 square root of 1 plus 4RC squared. Then plus, because our input signal is this. I think that's, do I want to do that? No, that's minus. I think that's a minus. 2t plus 1 over square root of 1 plus 4RC squared. Angle positive. I think that's going to be a positive. Yep, because I think it's, is it a positive? Yep, it's going to be a positive. Tan 1 plus 4RC squared. And then that's going to be a plus 2t. There we go. I think I'm doing it right. But you notice that this is e to the that, and then this is e to the that, and these are pluses. That means you're going to have 1 plus over 4RC squared cosine of tan minus 1 of 1 plus 4RC squared plus 2t. I think I did this math right. There we go. I think that's correct. Actually, I actually didn't even check my notes. Yeah, I think that's actually correct. Yes. There you go. Oh my gosh. Whew. And that's your final solution. So hopefully this was really good review. I kind of feel bad that I didn't make the first video for digital. I heard it was kind of whack, but I know you guys will do strong on this analog. And trust me, if you go over these notes, you guys will be great. So with that, take care and have fun. Oh, it's not playing my music. That's okay. Oh wait, that's cuz. Okay. Take care, y'all.